So Unit 9, all we're really going to deal with is solving tougher differential equations. We've already been solving differential equations, but they're going to get a little more difficult. Okay? And a quick example of like a differential equation, if we want to show you, is like, hey, a derivative is equal to 2x, and I'll say like f of 0 is equal to 4. I ask you to solve that differential equation. What's the thing that you have to do? What do you have to find? Yeah, you have to find c, but finding c is like giving you your original function. So you like take the antiderivative of this, and you get x squared plus c, and you could say that's equal to y, or you could say that was equal to f. And then we find c by using that information, right? Okay, that's solving a differential equation. Well, the functions aren't going to stay this easy. Okay, the differential equations won't always be with just x's. Sometimes they'll be with y's, like that. And all of a sudden, things will become more difficult. So what we're going to deal with now is, what if we have antiderivatives like this, and I can't take the antiderivative? We're going to find out a method to take antiderivatives of tough-looking functions. And we will use this method called U-substitution. Method to take antiderivatives of tougher looking functions. Okay. In particular, the tougher looking functions have to be specific looking, because U-substitution will undo the chain rule. Okay, so we learned the chain rule to find derivatives. Now we will find that U-substitution will help undo the chain rule to get us back to where we started. So let's remember the chain rule. Okay, chain rule is just a rule for derivatives of compositions of functions. The derivative of f of g, this composition of functions, is just the derivative of the outside. Leave the inside alone, times the derivative of the inside. Okay? So we can take the derivative of these three functions, right? So let's do that. We get negative sine 2x times the derivative of 2x here. This is like x cubed plus 1 to the 1/2. You don't need the square root. So using the power rule of derivatives, it'd be 1/2 x cubed plus 1. You'd subtract 1 to the negative 1/2 times the derivative of the inside. This would be 3x squared. And I can rewrite that to be 3x squared over 2 root x cubed plus 1. And then the last one, instead of distributing this and taking x squared plus 1 to the 4th power, which would take a while to do, I'll use the chain rule. And I'll say, okay, that's 4 x squared plus 1 cubed times 2x, or 8x times x squared plus 1 cubed. Okay? We got those, right? Any questions about the chain rule and taking the derivatives using the chain rule? This is all review. Well, today, we're going to start here and go backwards. We will be doing this to get our answer of this. We will be taking the antiderivative of this to get our answer of this. We will be taking the antiderivative of this to get the answer that. Okay? And here's why. The reason why is because these look like this. I can take something that I know looks like this, f prime of g of x times g of x times g prime of x. I can say, oh, if I know it looks like this, I can easily turn this into f of g of x, so long as I know what's what. Let me show you what I mean. This 2x and this 2, this is kind of g of x. This is g. This is g prime. And this is f prime. I take the antiderivative of f prime. I get f of g. Let's look at this. This is actually g in here. You can see this is g prime, and turns out this square root function, this is f prime. Well, I can take the antiderivative of this f prime, which is, something to the negative 1/2. The antiderivative becomes f, and look at that, that's g right in here. Here, this would be considered your g, this is your g prime, and then this would be your f prime. Well, look at that. That turns into f, and that turns into, well, that stays as g. You see that? We are taking something that looks like this, and we're turning it back into this. Now, you might be like, ugh, I don't see that, Mr. Messner. That's really confusing. Well, don't worry. There is a process. There is a technique to do this. And it'll take some practice to kind of be competent at the technique, but you'll see that it's actually not that hard, okay? But first things first are like, we don't have to know this U-substitution technique to undo the chain rule. I could give you something like this. You should be able to find the antiderivative of this just by figuring it out. So figure it out. What do we get? Yeah, exactly. 1/3 sine of 3x. We know that we're going to have sine of 3x, right? But then if I take the derivative of sine of 3x, I get cos 3x times 3. So I kind of have to get rid of this 3 by adding a 1/3. And all of a sudden, that 1/3 and that 3 goes away. So boom, you just undid the chain rule without U-substitution, without a special technique. Okay? So for some of these questions that you'll see, you can use this technique you're about to learn, or you can just figure it out. Okay? I'll show you that most of the times, though, in the examples I'll show you, it'll be tough to figure out. Okay? So let's go over, really, how this technique looks like. Okay? Let's figure out U-substitution. Okay, it's a multi-step process, so leave some room here. Okay, I'm trying to take the antiderivative of f prime of g times g prime with respect to x. What is my answer going to be? What is the antiderivative of f prime of g times g prime? F of g of x plus a c. So on the bottom here, I'm going to show you that my answer is going to be f of g of x plus c. We're going to get there, but it's not going to be obvious how we get there, okay? We're just going to get there. All right. Leave room for step 0. We're going to come back to step 0 later. Step 1, we will set u equal to what is g of x. G of x is typically the inside of a composition of functions. If I have a function that looks like f prime of g of x is the inside of a composition. Now, that's not always the case, but typically it is. Okay? And what you're going to do is to the right of whatever you're doing, you'll say, okay, u equals g of x. Step 2 is you will take the derivative of u equals g of x with respect to x, which will give you something I'll show you in a second. d dx u equals g of x. Now, I'm going to show you what I mean by doing that. I'm going to show you what your answer is going to look like and what you'll need your answer to look like. Okay, so you don't have to show this step, but watch what happens. I'm going to take the derivative with respect to x of u equals g of x. Now, let's look at the left side. What is the derivative with respect to x of u? Exactly. The variables don't line up. So like the derivative of u is 1, but then you need the du dx because of the chain rule. The derivative of g of x is g prime of x. Okay, now this is what we want to do. However, what we're going to do is a lot of substitution here, and I'm going to substitute for dx, so I'm actually going to move dx over to the right side by multiplying both sides by dx. Giving me du is equal to g prime of x dx. Now, I'll tell you right now, this step that I showed, you will skip. As long as you understand exactly what's going on. Okay? So, after you take the derivative of u equals g of x, I want you to show your answer as being du equals g prime of x dx. Let me move that down. Okay, so this step here I'm going to shrink, and you don't have to show it every single time. It's not necessary. But it's there. Okay, the next step is to solve for dx. Write this down. This stuff you will forget. So we will have g prime times dx. So I will divide both sides by g prime of x to give me dx equals, you can either say du over g prime, but I like to just leave du by itself and have 1 over g prime for simplification's sake. All right, here's the key step. Sub in u, sub 4 dx. Leave everything else alone. Okay, we will take u, and instead of g of x, I'm going to make it f prime of u. I will take what dx is equal to and replace dx, just dx, with whatever it's equal to. Giving me, this will turn into the antiderivative of f prime of u. G prime of x is going to stay. Dx will turn into 1 over g prime of x times du. Dx goes away. Step 5 is the next key step after you substituted in u and you substituted for dx. Stuff should simplify. Your new equation that you're taking or your new expression that you're taking the antiderivative of should only have u's. Okay, so I'll say stuff should simplify. You should only have u's. It should simplify to an easier equation, to a, I'll put in quotes, a simpler equation. Not equation, I keep saying equation. Simpler function or antiderivative. With just u's. Watch how that happens here. The g prime of x cancels with this g prime of x. That simplified, this leaves me with just f prime of u du. Well, with this simpler expression, we will be able to take the antiderivative of. It'll just be obvious how we can take the antiderivative of f prime of u. So what's the antiderivative of f prime? F. This turns into f with u's plus c. Du goes away, of course, because this is the antiderivative of f prime with respect to u. This is the antiderivative of f prime with respect to u. Well, we need to get to our answer all the way down here. F of g of x plus c. How do we do that? Yeah, u is equal to g of x. We'll substitute back in g of x. That's the last step. Sub back in g of x. All right. Let me show you how that's going to work. For this previous example that you guys did by yourselves without using this technique, I'll show you the same example using the technique. Okay? But then, all the other examples, you won't be able to figure out yourselves, I guarantee. You'll have to use this technique, okay? So here's what I do. I see cosine of 3x dx. I see we have a composition of functions here. Since there's a composition of functions, I'm saying, oh, this looks ripe for U-substitution. I will set U equal to the inside of that composition of functions. Typically, it's going to be the inside. Then I'll take the derivative with respect to x, giving me du is equal to 3 dx. That's the whole. We had du dx is equal to 3. Multiply both sides by dx. Then I will solve for dx. Divide both sides by whatever dx is being multiplied by. Then I will substitute in u. Got there. I will substitute 4 dx, giving me a simpler function with just u's, cosine of u, and then this is 1/3 du. And if I want to rewrite it, I can. 1/3 cos u du. Now, of this simpler function, I can take the antiderivative of that simpler function, which gives me 1/3 sine of u plus c. There's my antiderivative. And then, of course, I can sub back u in 1/3 sine of 3x plus c. The same exact answer that you figured out, just using this technique. Now, am I going to tell you that you have to use this technique to take the antiderivative of cosine 3x? No, I just want you to get the answer, okay? I'm just showing you that this technique also works for this. However, for the next couple, you probably won't be able to figure out by yourself the antiderivative of it. So this is where U-substitution is really like required. Okay, so let's give this a shot. I want you guys to kind of struggle through this yourselves. First, step 1, set u equal to g of x, which is typically the inside of a composition of functions. I see a composition of functions here. I see a square root over a function. Set u equal to typically the inside of that composition. Step 2, take the derivative with respect to x of that inside. Now, you should end up with du is equal to your derivative dx. That's the whole kind of, we want things to look a specific way so that we can substitute back in. Step 3, substitute in u, substitute 4 dx. That should create a simpler looking function that we can take the antiderivative of. Then take that antiderivative using your regular antiderivative rules. Once you find the antiderivative, go ahead and sub back in g of x. See if you can figure it out. Check your answers with a neighbor. All right, here we go. U is equal to 4x plus 3. I took the derivative and I manipulated it, so I had du is equal to 4 dx. I then solved for dx. Dx is equal to 1/4 du. Then I substituted in u, oops, not 4, substituted in u, and I substituted 4 dx. So that I got the antiderivative of the square root of u, not 4, u, times 1/4 du. Now, this is a simpler expression that I can take the antiderivative of. It's the same as taking the antiderivative of 1/4 u to the 1/2 du. I take that antiderivative, I add 1 to this power, making it u to the 3/2. I multiply by the reciprocal, that's 2/3, which I'll multiply by 1/4, plus c, which gives me 1/6 u to the 3/2 plus c, which gives me 1/6 4x plus 3 to the 3/2 plus c, when I sub in 4x plus 3 back for u. Questions? The more we do this, the better we will get at it. So let's do another one. Step 1, set u equal to g of x. G of x is typically the inside of a composition of functions, the entire inside of a composition of functions. We just had a square root in the last one. There's a square root here again, so maybe we're good for this one. Then take the derivative with respect to x of u equals g of x, giving you du equals g prime dx. Substitute in u, substitute 4 dx. Stuff should simplify so that you just have something with u's. This 3x is going to stay here. It will go away through the simplification. That's really g prime of x, which will cancel with the 1 over g prime of x. Negative 2x. Negative 2x. xx. They'll cancel. We need stuff to cancel so that we just have something with u's that we can take the antiderivative of. I'll give you another couple seconds and I'll walk you through the key steps. This x. We need something with just u's, so we need to get rid of those extra x's. I need to get rid of that 3x, or really just that x, so that I just have u's. It will cancel so long as everything is set up correctly. We'll find out. Is everybody here? Does everybody have negative 1 over 2x du? We're good there? Okay. This goes for dx. This goes for 9 minus x squared. Watch what happens. This is 3x root u. This is 1 over negative 2x du. Since this is all multiplication, I can multiply anything by anything. I can multiply the 3x by the 1 over negative 2x. Guess what? The x's will go away. We need this to happen, or else we either made a mistake or the problem is not set up for you to solve and find the antiderivative of using U-substitution. Once the x's do go away, now I have this simpler function with just u's, negative 3 halves root u du. Now I can take the antiderivative of this. This will be u to the 3 halves. I'll multiply by 2/3 by negative 3 halves plus a c. All of a sudden, the 3's cancel, the 2's cancel. I'll just have negative u to the 3 halves plus c, or negative 9 minus x squared to the 3 halves plus c. Okay, remember, antiderivative of the square root of something, add 1 to the power, multiply by the reciprocal. So this is u to the 1/2. We add 1 to make it 3 halves. We multiply by the reciprocal. Okay? Now, even if you didn't get that one, that's okay. You're going to get this one. What is the antiderivative of x squared, x cubed plus 3 to the 5th? Check your answers with a neighbor. Good. Times 1/6 times 1/3. All right, we set u equal to g of x. We then take the derivative and manipulate it a little bit to get du is equal to 3x squared dx. We then will solve for dx. If all is right in the world, when we substitute in, we'll have a simpler function with just u's. I notice that the x squareds will cancel. All is right in the world, giving me this simpler expression that I need to take the antiderivative of, which is 1/3 u to the 5th with respect to u. Well, that's going to be 1/3. Add 1, that's u to the 6th, times the reciprocal, that's 1/6. Multiply those things together, and that's plus a c, and I get 1/18 times x cubed plus 3 to the 6th plus a c. Mr. Ryden. Yes, we will see that in a couple seconds. If the x's don't cancel and you end up with something, if this is like x still after you cancel x squareds, well, either you messed up or you can't take the antiderivative of this. That's the situation. This is only for specific looking functions that look like this. G, f prime, g prime. And we are undoing this to look like f of g. And then, of course, we have these constants that like kind of trip things up. But this is f of g. This is f prime of g times g prime. This is like the derivative of the chain rule. This is your initial composition where we take the derivative of. All right, try this one. Cool. Everything is right in the world. I get a simpler function that I can take the antiderivative of. That's 1/4 sine of u. The antiderivative would be negative cosine. So negative 1/4 cos u plus c, which is negative 1/4 cos x to the 4th plus c. How do we do? Getting better and better. Good. Well, they're not always that straightforward. Like that. You'd think, right? You'd say, okay, u is equal to 2x. I get du is equal to 2 dx. I get dx is equal to 1/2 du. Well, I got sine u cos u 1/2 du. Is this a simpler function that I can take the antiderivative of? No. So it turns out this is one of those cases where we don't set u equal to the inside of a composition. Turns out this is a composition like in another way. Maybe like that. And really where we can see it is, hey, if this is like G, this is G prime. And it could be the other way around too, actually. But if you see, oh, that's the derivative of that, well, I set u equal to this G, and then I will be able to cancel this G prime. Try it out. U is equal to sine of 2x, go from there. What you'll find is that the more and more you do these problems, the more and more you'll be able to see what you should set u equal to. By examining the expression, by seeing, oh, that's the derivative of that, so I should set u equal to, you know, the antiderivative, this thing whose derivative I can see. See if you can do it. Mr. Martin.
What makes you set u equal to sine of 2x? It would be completely wrong if you ended up setting it u equal to cosine of 2x.
No, it would have worked. Only in this situation, yeah. Okay. The key is like the function, the f prime is just like x. And this is really like sine to the first power. So it's almost like this is the inside of a composition, but the composition you can't even see is like something to the first power. That's f of g times g prime. And I could have done it the other way. I could have said this is f of g and this is g prime. Only in this situation you can kind of flip-flop and do it either way. But do we understand how we get here? I set u equal to the thing that I know when I take the derivative of, I'm going to be able to cancel. So I see I can take the derivative of sine of 2x, I'll be able to cancel cos 2x. Because the derivative of sine 2x is cosine 2x times 2, I then solve for dx, I divide everything, I get dx equals 1 over 2 cos 2x du. Substitute that in, u goes for g, cos 2x stays, dx turns into 1 over 2 cos 2x, cos 2x cancel, we just have 1/2 u. I take the antiderivative. The antiderivative of u is just u squared over 2, or 1/2 u squared. So this is u squared times 1/2 times 1/2, that's 1/4 u squared. That's 1/4 sine of 2x squared. Cool? All right, well, you try another tough one. And we'll skip this one. We don't have time to get there. Oops. The key is to be able to see, if I take the derivative of something, maybe it's the inside of something, maybe it's the entire thing, I'll get something else I will cancel. Everybody look at it and take a guess as to what I should set u equal to. Good job. Tangent is correct. Because this is tangent of x to the 4th power, and I can see that this is the derivative of tangent, so this is g prime, this is g, this has got to be f. So set u equal to tangent. And go from there. Derivative of tangent is secant squared. Aha! That's going to cancel those secant squareds. That's going to make my function simpler to take the antiderivative of. Boom, boom. I'm good here. 1/5 u to the 5th plus c 1/5 tangent to the 5th plus c. All right, let's try another one. Do this one on the left. What are our guesses? What should we set u equal to? T minus 2t, let's try that. T minus 2 over t. I get du is equal to 1 minus derivative of this would be negative 2, so this would be positive 2 over t squared dt. I then have dt equal to 1 over 1 plus 2 over t squared. Is that going to help me when I plug in? Probably not. Okay, so maybe let's try something else. What else should I try? Maybe t squared. Let's try t squared. du is equal to 2t dt. Let's see, dt is equal to 1 over 2t du. Let's see what happens. I get u. I get t minus 2 over t, and then I got 1 over 2t du. Is that going to simplify with all these t's in here? Nope. So that doesn't work. So what do we do now? Set it equal to t? Well, that's not going to cancel it. No. It'd be u minus, it would just pretty much make it the same thing. So, be careful. After you learn this technique, you're going to think you're going to use it in all situations. Do not. Step 0, go back to your instructions. Step 0 is to always attempt to simplify first. This is the most important step. Because just because it looks complicated doesn't mean it will remain complicated. All I need to do is distribute t squared, and I get t cubed minus 2t dt. Well, guess what? I could take the antiderivative of both of those. That's 1/4. Oops. That's 1/4 t to the 4th. Minus t squared plus c. Right? Piece of cake. Same with this. You're going to look at this and you're going to be like, man, I got to use U-substitution. This looks really complicated. No. Divide both of those terms by the square root of x, and you get x to the 1/2 plus 4x to the 3/2. I could take the antiderivative of both of these. This is 2/3 x to the 3/2. This is 5/2, 8/5 x to the 5/2 plus c. So remember that for your homework. Don't always assume U-substitution will work, okay? What we will also find out, but you'll not be given questions like this, is that sometimes you'll think you can take the antiderivative of anything. You won't be able to. It's only for these specific looking f prime of g, g prime functions that you'll be able to do it. Okay? Like this. U-substitution does not work here. It's just that. Have a great long weekend.